Welcome back to Wrench Works. I'm Jenny. And I woke up to a balmy negative 10 degrees outside this morning and an excellent question in my inbox. The question was, hey Jenny, is it really necessary for me to run a warm-up program on my CNC mill? I love this question so much, so let's talk some shop, shall we? The truth of the matter is, you could take 100 machinists, tool and die makers, and engineers, and chuck us all in the same room and pose that question. Chances are pretty good that what you're going to end up with is a variation of about 100 different answers. You're probably wondering, well, why is that? Isn't there one cut and dry answer to this question? And honestly, not really. The reason being that there is such a variety of different applications, materials, and machines, and it's not a one-size-fits-all box. So what I'd like to do is break down my 25 years of experience, what I've noticed, what works, what doesn't work, and kind of the protocol that we follow here at Wrench Works, and see if you can kind of find your own way of starting up that machine and warming it up. I'd like to start with one of the biggest variables first, and that is going to be ambient room temperature. Now, when you really think about it, everything in your shop is touched by temperature, from your equipment to your materials, as well as your metrology tools and your staff. I firmly believe that climate control is one of the best investments that you can make in your shop. Now, here at Wrench Works, I like to keep everything here at a consistent 72 degrees. Now, it's not the temperature that really matters. 72 is not some magical number. You could keep your shop at 68 degrees. You could keep your shop at 76 degrees. The key here is going to be consistency. Why? Because most of your equipment is going to be made out of metal, and there's going to be thermal expansion and thermal contraction with temperature fluctuations. And the same thing kind of goes through your material. If you're working on, say, a high tolerance part, like a mold, your materials are going to expand and contract with temperature swings. And what happens is you end up having to chase that thermal expansion as you're doing your measurements, as you're doing your cutting. And it's a lot of extra time that you're essentially wasting when you could keep everything consistent and normalized and not have to spend quite as much time saying, okay, this block has expanded a little. Am I going to potentially overcut on my next machining operation? One other important note that I'd like to make about climate control in your shop, and to me this is especially important if you live in the Midwest like myself. So here in Wisconsin, we are prone to some pretty drastic temperature changes throughout the day as well as from season to season. And what can occur between all these massive temperature swings is you're taking the air, you're cooling it, you're heating it up, you're cooling it, you're heating it up. And what can happen is you start developing condensation, both on your equipment and your materials. And that condensation is not doing your equipment any favors. You can start to see electronic failures, and you can develop rust on your equipment and its critical components. So to me, when I look at climate control, I also look at it as a way to take care of the investment that I made in my equipment as well as my materials, supplies, and tooling. We're going to use my buddy Sven for this next segment for a couple different reasons. So first of all, Sven always feels just a little bit left out because the majority of my work does tend to be mill work. Second reason though, my guy Sven here, he's one of those guys that leaves his junk all hang out. And therefore, he's going to give us a really good visual illustration of the next topic, which just happens to be fluids and lubricants. In my shop, there's really only 3 basic kinds of fluids or lubricants that I really even need to concern myself with. Let's first talk about the spindle. And if you watch my drawbar episode, you'll probably remember me saying that I have a drop-in unit that I'm going to be putting over an Ollie there. Now, the spindles that I have in my machines are sealed spindles. And what that means is they pre-pack the bearings and the races with grease. There are no zerks. There's no way for me to add additional grease. There's really no need for it. However, grease does degrade after a while, and you'll start noticing a lot of heat coming from the spindle. You might notice some noise. There's a pretty good chance that means that your grease is degrading. And in this case with Sven and Oli and my machines, my only options are really to send in the spindle to get it repacked and the bearings replaced, or the cheaper, quicker option, which I do tend to go for, which is just simply replace the whole drop-in unit. It's really not terribly expensive because my machines are not big, expensive industrial machines. They're kind of little guys, so I tend to go that route just because it saves me a lot of time, and honestly, I don't want to be chasing around the little balls that are inside the spindle. Next item is going to be coolant. Now in Sven here, we do have him outfitted with a flood coolant system. The coolant's purpose is to just flow over the workpiece as well as the cutting tool. It kind of serves two purposes. So the coolant that I have in this machine, it's Qualichem, and what it does is it not only keeps the workpiece and the tool cool as it's cutting, it also serves as a lubricant so that as you're cutting, that chip doesn't want to stick to the cutting piece, and it flushes it out, gives you a little better surface finish, and also preserves your tooling. The third item is the one that I tend to be most concerned with, and that is my whey lube. Now, the whey lube, in my case, I have a little manual oiler here, and you'll see all these little lines that are kind of running through, and there's some manifolds. Those are an oil delivery system, and what this whey lube does is it keeps all the slidey bits lubricated so that any of your sliding surfaces don't end up galling, because when you think about it, everything here is steel, and if you're running it dry and it gets heated, things expand and things want to gall up or run real tight on you. And so that's going to be the purpose of whey lube. And what I'd like to do is get a little bit more in depth with this so you can kind of see what we're oiling and how this functions. I hope you have a good clear shot here, because what I want to do is not only just cover what the purpose of whey lube is, but give you a real brief introduction on some key components in a machine tool that you have maybe heard about, but we're not quite sure what their purpose was. So when I pull that manual pump handle out, what I'm doing is delivering a lubricant to the sliding mechanisms in the machine, and you can see all these manifolds and oil lines that kind of wrap their way through. What they're doing is feeding the dovetail ways and the gib, which we'll get back to that in just a moment, as well as the ball screw. And there's a ball screw up here, and you can probably see this one just a little bit better. And so when a machine tool moves, it's actually sliding along this dovetail, and you can kind of see it sliding along the dovetail. And if I move the Z-axis, if you pay attention here, you'll see that ball screw is actually turning. And the ball screw is what conveys the motion from the motor to the actual axes. We're going to scoot back over here, though, and talk for just a second about a gib, because you might have heard someone talk about gib adjustment. And what I tend to notice is people really overcomplicate the process. So all a gib is the gib is this little wedge-shaped piece of metal that sits between the dovetail clearance and the carriage or whatever item it's sliding on. And all that does is you can tighten it. It's tapered, and you either shove it in further to give it more resistance, or you back it out so you get a little more play. All a gib does is kind of tighten up the slack in there, but you never want to over tighten a gib, because that can introduce galling as well as stutter stepping on your axes. So basically, this whey lube is just keeping all those slidey bits, the ball screws, the ways, and the gib lubricated, so you're not metal on metal and you're not galling or creating additional heat as you're moving the machine tool. There may be a few people thinking, well, Jenny, this is all well and fine, but I thought this episode was about machine warm-up. And it is. I'm getting to it, but it is all interlinked. I would, however, be remiss if I left out my brothers and sisters in the trade that have no choice but to leave their machine tool in a non-climate controlled building. There's a lot of folks that machine out of their outsheds in their backyard, and there's no judgment here, and we've all been there. So what I want to cover is a little bit of what to do if you do have to leave your machine out in sub-zero temperatures. Starting with the spindle, as I've mentioned, I have a sealed spindle. It's an air-cooled spindle, and there's not much I can do about the grease inside the spindle other than run kind of a standard spindle warm-up routine. Coolant. I've had a lot of questions on coolant. What is the freezing point of coolant? So now that is going to vary from manufacturer to manufacturer, as well as how well you mix it. Remember, if you add more water than recommended, you're making your coolant lean and more prone to freezing. However, if you run it too rich with more coolant mixture than advised, it can actually be pretty hard on your paint, your powder coat, and it can get a little sticky, and you're also wasting money because there's no reason to run it at a much richer ratio than is recommended. Now, here in my shop, we run Qualichem Extreme Cut 251C. And taking a gander at the MSDS sheet, it tells me that the freezing point is anything below 40 degrees Fahrenheit. Boiling point is anything above 212 degrees Fahrenheit. Now, what does that mean? Does that mean, Jenny, if the temps drop below 40 degrees, am I going to come out to see my coolant is completely frozen solid? Not necessarily, but it's not going to have that free-flowing consistency. It's probably going to closer resemble the consistency of, say, a brandy slush. So there are a few things that you can do to kind of help protect your equipment without having to constantly go back and forth and empty your tank every night. Now, if you live in a region that is going to go through a prolonged cold snap and you're going to be leaving your machine sitting for a while, I do have a couple recommendations to help you keep your machine in tip-top shape without adding a whole lot of extra work on your end. So I start with coolant hoses. I do like to at least blow out the coolant hoses if I do have a bunch of coolant in them. Reason being, if that coolant does freeze solid into your coolant delivery system, it can expand and it can just crack and break your hoses and your lines. And so for me, it's just kind of a little safety assurance. It takes a minute. You just unplug the hose and shoot some air through it just to make sure that you get the bulk of that fluid out so it doesn't expand and crack your coolant system. Now, coolant tanks. Anyone who's done a coolant tank swap or has done the maintenance on their coolant tank knows it's a pain in the butt to have to haul that big giant coolant tank in and out and swap out the coolant. It can get expensive. So what I recommend, and I realize this is kind of a corny little trick, but has worked for me in the past, is get yourself a really inexpensive aquarium bubbler. They use those a lot in man-made ponds. If you have a carp pond, if you have a turtle pond in your backyard and you happen to live in the Midwest, you're probably no stranger to this. It's just a pump that sits in there and bubbles the water. And what it does is agitate the water so that it's less likely to freeze over longer cold snaps. And I wanted to add this as well. With the aquarium bubbler, it not only helps prevent your tank from freezing, but it's awesome for preventative maintenance when it comes to coolant condition because anaerobic bacteria tends to develop underneath a layer of tramp oil or excess whey oil that circulates its way down to the tank. And what this does is it keeps that water agitated so anaerobic bacteria doesn't have time to grow. Your coolant will stay fresher longer and your shop will smell better in the long run. On to the lubricants. So in all of my machines here, I run an ISO VG68 whey lube. What does that mean? Well, it just means in optimal temperature ranges, it has a viscosity of about 68, and it also has additives that kind of help prevent wear and tear on my machine slidey bits. Now, there are two temperature ranges I want to focus on here because people always kind of get them a little discombobulated. There is a freezing point and there is also what's called a pour point. So the freezing point is when you can anticipate your whey lube is going to start freezing. And on the whey lube that I run, it's about 5 degrees Fahrenheit. The pour point is where that viscosity really starts thickening up and changing. And the pour point for the whey lube that I run is at 40 degrees Fahrenheit and below. You can start seeing kind of that flow rate change a little bit. So My recommendation is if your whey lube does freeze, you're going to want to warm up your ambient temperature a bit just to kind of get it flowing. And then once you kind of get to the point where it's starting to flow somewhat regular again, then you can start kind of pumping it through it while you're doing your warm-up cycles. So we're getting close to the warm-up cycles. I just got one more topic and then we'll slide right into it. All right, so we're going to start putting all this together, and I'm going to give you the justification as to why I tend to run warm-up cycles in my shop. So when I'm thinking warm-up cycles for a machine tool, I'm not really necessarily thinking of it in terms of temperature even. What I'm thinking of is thermal expansion of the components within the machine and how to normalize them as well as stabilize them. So as I'm machining, the results that I'm getting are going to be more predictable in the long run. Let me explain. I went ahead and pulled back the Y-axis bellow cover on an old Ole here, and there's a couple things I wanted to point out as we're taking a look at his ball screw. First thing you'll probably notice is you can see Ole's ball nut right here, and around that ball nut is actually a housing. That housing is bolted onto the bottom side of the saddle, so that as the ball screw's turning, that saddle's transversing along this ball screw. Other thing that you may notice is beyond the nut, you'll just see that that ball screw is kind of hanging out into space here. And it's not an issue because I know I have a less expensive machine tool, and I have found ways to kind of circumvent some of the accuracy issues that I may have on a machine with this kind of design. So what I want to do is give you a little closer look at a ball screw while it's not in the machine. We're going to be covering ball screws in much greater detail in a later video, but I figure for now I at least want to give you a little bit of a visual so you can kind of put everything together as I'm talking about ball screws, thermal expansions, backlash, that kind of thing. So this is a ball screw, very similar to the style that I have in Ole. This is the screw itself. This is the ball nut. And the ball nut turns along and transfers along the screw via some ball bearings that actually ride into these grooves. Now, when you look at the ball nut, you'll see these little divots here. Those are actually ball returns. So what's happening inside the ball nut is the little ball bearings are riding along the groove and recirculating. This particular style, you'll probably notice there's a little spacer in there. This is called a double ball nut. And double ball nuts are actually pretty awesome because they have what's called preload. And what the preload does is you've got two nuts that are kind of back to back. And what it does is reduces the amount of axial play in the ball screw. So you have the two nuts that are kind of counteracting against each other. Now, when you get to higher end machine tools, you'll probably notice that some of them are actually supported on both ends. And not to be confused with preload, those are called pre-tensioned ball nuts. And what they do is they kind of stretch the screw a little bit, which reduces the effects of thermal expansion on it and gives it a little bit more rigidity and repeatability. Now, I don't have that in my machine, but that's why I do the warm-ups. And a couple other things I want to point out, this is going to be the motor end. So on the motor end, the motor is actually coupled to the ball screw. So as the motor turns, the ball screw turns. You'll see in a lot of other larger machine tools that there might be a couple extra nuts here as well. And those nuts are used for what's called angular contact bearing adjustment, which basically means as this screw wears, you can still make up for some of that slop, or what some people call backlash. That's kind of the technical term for it. So when you hear the term backlash, you're thinking slop. It's basically the extra gap in between the balls and the grooves on the balls. And so what you're doing with this angular contact adjustment nut is you're putting a little more pressure on it. So you're reducing that gap a little bit. So as it moves, it doesn't have that slop caused by the wear. Now, ball screws are a consumable item. So chances are if you have your machine tool for a very long time and you run it quite a bit, you might eventually have to do a replacement on your ball screw. But again, having the ability to adjust it with angular contact bearings, as well as having a preloaded ball nut, does kind of help. When we talk about stabilizing the machine tool, I just want to let you know when and if I do any of my adjustments to the ball screw, via the angular contact bearing. I like to have the machine warmed up for that because we do have this end that's unsupported, and because this side's closer to the casting, it's going to have a little bit more heat. It's going to take a little bit longer for that heat to dissipate through here, and you can get a little unevenness there. So again, this is a really oversimplified way to describe this, but I just kind of want to give you a visual of what we're talking about and how thermal expansion affects the motion of your machine tool. Okay, onto the spindle and the casting. So if you watch my drawbar video, you probably recall this is the spindle motor and this is the spindle itself, and they work together via a belt and pulley system. The spindle motor can generate up to 10,000 revolutions per minute on this here spindle. And this spindle happens to be what's called an air-cooled spindle, which basically just means the only way that it can cool down is via the air around it or the ambient temperature of the room. There is no auxiliary chiller, there's no water cooling, it's relying on the air to cool it. And this spindle motor and this spindle can generate a fair amount of heat. Well, what happens to the heat that doesn't dissipate into the air? If you notice, the spindle motor and the spindle, they are bolted into the casting. So some of that heat is going to go into the casting. You're thinking, well, what does that mean? Well, what is the casting made out of? Casting's made out of metal. So what happens to metal when you heat it up? Well, it expands, gets a little thermal expansion. So what does this mean for your setup? As the spindle warms up, you could experience what's called spindle growth. And what it is just the metal in the spindle itself kind of expanding a little bit. And it can also reach the tool holder itself as well as the tool. And so the reason I warm up a lot of the times, especially when depth is critical, is if I were to come down here and start up my cold machine and touch off, say, a mold, and depth is going to be critical, I'm going to go touch off on that mold parting line or whatever feature I want. As it warms up, if that thermal expansion reaches down to the tool, what you're going to get is overcut because that tool is actually growing. And so even though you touched up here, the tool is actually going to be down a little bit lower as it grows, and you can actually cut a lot of those cavities just a wee bit too deep because the machine wasn't normalized when you touched off. Now, there's another factor that a lot of people really don't think about, but the head where the spindle and the spindle motor are bolted are actually, it rides along the column of the machine, and Ole is what's called a C-style casting. So when you think about it on a side profile, here's his head, here's the column or the Z, what the Z rides up on, and then we have the base. So it kind of makes a C. So that heat is in the head, but it can actually go down to the casting or the column as well. And when you get heat there, it can actually kind of tip forward as the two surfaces are kind of expanding. So now when you're cutting kind of down this way, the head might be slightly tipped due to thermal expansion, and that can throw a whole ball of wax into high tolerance parts. I'm going to stop for a brief recap because I know we covered a lot of material here. And basically, I'm going to tell you the three main reasons why I run warm-up programs. First of all, I warm up the machine to normalize or stabilize the machine components so that I can establish consistency in the areas that may be affected by thermal expansion. Number two, I also do it prior to making any major mechanical adjustments to my equipment to make sure that I'm not over adjusting and that I am taking into account that thermal expansion that does occur when running a machine tool. And lastly, I like to run it because it allows me to evenly distribute the lubrication on all the slidey bits of the machine tool. Now let's talk about programs. Tool paths for warm-up programs. So this is not a hard, fast science. Everybody kind of does it their own way, and a lot of machine tool companies already have those preloaded into the controller when you get them. Mine did not, and so I tend to make my own warm-up programs. Now for me, it's really important that I distribute my lubrication through all the extremes of the machine tool, and I like to get her good and warmed up. So I generally run her about 20 to 30 minutes in the morning just to make sure everything's all kind of a consistent temperature and that I have that lubrication evenly dispersed. So how I created my warm-up programs is I basically just modeled in a box in my CAD CAM system, And that box is about the same size as my work envelope. And I do a contour pass with the head ramping down at about 3-inch intervals per pass. It's not real fast on the Z. I don't need it to be. I like my warm-up program to take about a half hour. And the reason it takes a half hour is because I'm able to get multiple passes here. But as I'm doing each loop, I'm changing the RPMs on the spindle as well. And I like to start at the low range and work my way up to the high range. So on Oli here, his low range is 650 RPMs. And what I do is I tend to then step up each time it does these passes. So he starts at 650, then I rev him up to 2,000 RPMs, followed by 5,000, then 7,000, then wide open at 10,000. What that does is just kind of allows the spindle some time to get that grease warmed up. It allows the way lube to get distributed across the ball screws and the ways. And it also just kind of allows that spindle temperature to kind of normalize. So by the time I'm ready to touch off my tools, I don't have to worry as much that tool growth is going to cause me to overcut. So if you take a peek behind me, I currently have Oli running through his warm-up cycle. And you'll probably notice that that table is running the full range of motion, and that allows that lubrication to evenly distribute across all the little slidey bits. It also allows me some time to progressively ramp down in the Z-axis while that spindle's turning, and I like to, like I said, start at 650 RPMs, and then when it gets down to the bottom of that travel, it loops back up and goes to that next RPM range. And that allows my spindle some time to warm up. It also just kind of allows everything to heat up and work out any areas or uneven areas of thermal expansion in my machine tool. Again, there's no right or wrong way to do this. This is just kind of how I do it. I do also have one additional thing that I wanted to cover, because you probably noticed that I have some unusual little doohickey in the spindle. I never run my warm-up cycles with the tool in it, and I want to show you why. If you caught my drawbar episode, you probably remember this little guy. So this is the R8 collet that's sitting up in the spindle, and this collet is what holds your tool holders. So this stem here is a 3/4 inch straight shank stem, and this bore here is 3/4 inch. And because I have a pneumatic drawbar, there's always some tension on this until I release it. When I release it, it releases the tension on it, and I can stick that tool holder right up into the collet. And then when the tension kicks back in, it actually cinches around that stem and makes it so it holds the tool holder in place in the spindle. Now, you probably noticed this doesn't look like a standard everyday tool holder, and it's not. So my friend Sammy made this for me several years ago, and he calls it a nightcap. Because I have a pneumatic drawbar, there's always tension on this collet. And what can happen is if you leave this thing empty and you shut down every night, you still have tension on that collet. And after some time, it can get a little deformed and sprung. And so this I stick in it every night to make sure that that collet holds shape. I also use it to run all my warm-up programs, and I want to show you why. All right, a little information about Oli's spindle here. If you recall in some of my previous videos, I talked about my stepper motors, and the stepper motors can receive feedback from the control, and they'll do what they can, but they have no way of relaying back to the control if they're struggling or they hit any resistance. And so it'll continue thinking that it's doing what it's supposed to do because the stepper motors have no way to tell the control that it can't do that. Same kind of thing with Oli's spindle. Oli's spindle does not have an encoder, which means if the spindle hits any kind of resistance, it's still got a command to keep going, and it's going to keep going if it can. And if it hits resistance, it might slow down or even stop, but then when that resistance is no longer at play, it's going to start back up again. So the reason this is a safety thing for me, and the reason that I use the nightcap instead of a machine tool, is because this almost got me a few times. I want to show you what Oli looks like when he's running at about 1,200 to 2,000 RPMs. Now, typically, you wouldn't be able to see what was going on up here because normally that spindle should not run with the spindle door open. However, I did override it for this example, just so you can see what we got going on here. So right now I am running Ole's spindle, and he does have bad bearings, so he's actually making some noise, but a properly functioning spindle is going to be pretty darn quiet. I'm running his spindle right now at 2,000 RPMs, and you'll notice that the drawbar is spinning along with the spindle. Now you'll probably notice you can see the spin in the drawbar a lot easier than you can see the spin in the spindle. Now I really don't like running my spindle empty at all because it's not great for the collet. It's really not great for the machine, but I want to show you about feedback and how the pneumatics are separate from the spindle itself and what can occur if, suppose, someone comes downstairs, says, hey, I'm going to turn on the spindle and warm it up for you, and you forget and you say, oh, well, I'm going to go ahead and throw in my Superfly or my tool and get facing on this job. Now, again, if you look there, that is spinning 2,000 RPMs, but it's awfully hard to see, and especially if you're running a dust collector or an air compressor, you're not going to always be able to hear that. So now watch what occurs when I hit that power drawbar real quick, and suppose I have a tool in my hand and I'm going to shove it up in the spindle. I hit it, it stops, I release it, and now it started back up again. Now mine is tipping forward and riding a little rough because I don't have that door shut, but now that spindle just picked back up again. It could be devastating if you have a tool in your hand, because as soon as you release that button, that tool is going to spin right up again with your hand on it or without your hand on it. All right, so I went ahead and I closed the spindle door and I put the nightcap back in, and I have her currently running right now at about 2,000 RPMs. And she's awfully quiet, and she's still really hard to see that spinning cap. But in this case, if I completely zone out and forget that I'm running a spindle warm-up program and I can't see it and I can't hear it, I can still reach in here, hit this, and by the time I touch that running empty spindle retainer, the worst I'm probably going to come away with is some pretty nasty friction burn. At least I'm going to walk away with all 10 digits in place. Now, I am not sure if these particular apparatuses are still in manufacturing or not. However, you can do the same thing with an empty set screw holder. I would, however, remove the set screw just because, you know, the threads can loosen up after a while. And the last thing you want are projectiles in your shop. But basically, just any kind of non-tool holding tool holder that you can throw in there while you're running your warm-up programs are going to be advantageous, especially if you have a machine that has a pneumatic drawbar and no encoder. I realized that we just covered a whole gambit of materials in this single episode, and I hope that you were able to walk away with one or two useful pieces of information that'll help you with your endeavor. Because after all, our mission here at Wrench Wench Works is to make CNC machining theory, tips and tricks accessible, fun, simple, and safe. And if you do have any other questions, comments, or concerns, or if there's something you'd like to see in a future episode, please, by all means, drop it in the comments below. I love to hear from you all. And if you like this content, feel free to hit like. If you want to see a little bit more of me, feel free to hit that subscribe button. Thanks again for watching, and we'll see you next time at Wrench Wench Works. Bye.